So this video, from the previous video, the previous two examples, we have these quadrantal angles, and it's fairly easy for us to find the sine and cosine values, functions evaluated at quadrantal angles. But what about when we have angles that are not quadrantal angles? For instance, if I wanted to find the sine of an angle whose terminal side was right here. All right, that's going to be a little bit more difficult because this distance isn't necessarily, I mean, it's 1 unit, but I don't know the coordinates. That x and that y coordinate, I don't know. So let's talk about some methods that'll help us figure that out. All right, what we're going to do is we're going to identify some pretty popular angles. One type of angle is a 45-degree angle. And all of the angles in our unit circle that are multiples of 45-degree angles but are in an actual quadrant. For instance, a 135-degree angle, a 225-degree angle, and a 315-degree angle, right? And so what I'm going to do is I'm going to try to derive how we come up with the sine and cosine of these angles. And so first, if I look at my 45-degree angle only, right, this kind of splits this xy plane in half, right, or at least that first quadrant, right? And what I want you to notice is that this, if I were to write the equation of a line, it would actually be the line y equals x. So that means basically this point right here is going to have an x value that is the exact same as the y value. And so what I'm going to do is I'm going to draw a triangle here. And I know since this is the unit circle that this hypotenuse of that triangle is 1. And I know that since this is on the line y equals x, the x coordinate and the y coordinates are equal. And so what I'm going to do is I'm going to say, okay, well, both of these are x, for instance, although I know that this really is a distance y, okay? But they're going to be the same, so I can call it x. Well, since this makes a right triangle, I can use my Pythagorean theorem that says if I square one side, add it to the square of the other side that makes my legs of my right triangle, that should equal the square of my hypotenuse. Therefore, I get 2x squared equals 1. I can divide both sides by 2. I get x squared equals 1/2. And I can take the square root of both sides. I get x equals, and I'll normally say plus or minus. I'm not going to say plus or minus right now because I'm in that first quadrant and those are both positive values. I know that the square root of 1 is 1, so I'm just going to write 1 right there. And that is really big. And the square root of 2, I'm going to leave it as the square root of 2. And that's big too. All right, I want to rationalize my denominator, and so I'm going to multiply the top and the bottom by the square root of 2 here. And so I'm going to get square root of 2 over, well, the square root of 2 times the square root of 2 is square root of 4. That is 2. So that means this x coordinate equals square root of 2 over 2. And this side over here, which is our y coordinate to that point, is going to be square root of 2 over 2. So the ordered pair I have here, square root of 2 over 2, square root of 2 over 2. Okay? And so if I want to know the sine of 45 degrees, it's the y coordinate, square root of 2 over 2. And it just so happens that the cosine of 45 degrees is the x coordinate, which is also square root of 2 over 2. Now, once I get this one, this 135-degree angle is very similar. It kind of splits this quadrant in half. And so this point right here is going to be very similar to the original point that I got over here. Except the coordinates are going to have, this is now a negative x value. So I'm going to have a negative square root of 2 over 2. And the y coordinate, I go up. So that'll be a positive square root of 2 over 2. When I come to my third quadrant to 225 degrees, my ordered pair on the unit circle where this terminal side of a 225-degree angle would intersect my unit circle will have a negative, because if I go from my origin, I go left or negative, and that's square root of 2 over 2. And I go down to get to that point, and that represents a negative y value. So I get negative square root of 2 over 2. And last but not least, if my terminal side is here, I get a positive because for me to get to this point, when I think about my XY plane, I go right one and, well, I go right square root of 2 over 2 units, and I go down negative square root of 2 units. And I'll have that point there. All right. And so I could find the cosine of 225 degrees by looking at the x coordinate of this angle, or this point where this angle subtends or cuts through the unit circle, and that's going to be a negative square root of 2 over 2. All right. And so that's how we find the sine and cosine of values that are multiples of 45 degrees that are in a quadrant. All right. Let's see what happens for another type of angle. Here we're going to look at a 60-degree angle, okay? And so what we'll notice, all right, I have a 60-degree angle here, right? If its initial side is on our positive x-axis here, and its terminal side is where we have our 60-degree angle. If this is a 60-degree angle, and let's say I were to draw a right triangle here, right? So I know that this is 60 degrees, and I know the 60 is here, but this part, this angle right here is 60 degrees. Remember that the sum of the interior angles of a triangle is 180 degrees, right? And so I have a right angle right here, which is 90, plus this angle that I drew is 60 degrees. And so that makes 150, right, together. And so I need 30 more in order for me to get to 180 degrees. And so this angle up top here is actually 30 degrees, okay? Remember, since this intersects the unit circle, I know this side length here, from the origin to this point right here, is 1 unit long. And so what I want to do is I want to find this side and that side. To help me do that, I'm going to get a little clever here. What I'm going to do, so I have my 60-degree angle here and my 30-degree angle here. I know this side length is 1. What I'm going to do is I'm going to draw a congruent triangle. If that's congruent, then that means this side here, or that angle there, is 60 degrees. This angle here is 30 degrees. That side length there is 1. Now, there are some properties of geometry. Now, I know this doesn't look like it, but if this angle here is 30 degrees and that one's 30 degrees, then this entire angle here is 60 degrees. Guess you can't see that. Which makes this an equilateral triangle, which means that this side length is 1 unit long. Now, since this side length is 1 unit long, and these two angles here and here are 30 degrees each, that means this side length here and this side length here are equal. And if they're equal and the whole side length is 1, then they're a half unit long each. So I get a half and a half. And so what I have right now in a 30, 60, 90 degree triangle, which I have here, I have this side length as 1, this side length as 1/2. I can use the Pythagorean Theorem to help me get the other side. Pythagorean Theorem says, square the legs, add them up. It should equal the hypotenuse squared. If I subtract 1/4 from both sides, I get 3/4. Take the square root of both sides. Normally we'll put a plus or minus there. I'm going to leave off the minus since I'm looking at side lengths of a triangle right now. But I know I do the square root of 3. Stays the square root of 3, but the square root of 4 is 2. And so this side length here is the square root of 3 over 2. And so this ordered pair, I go to the right 1/2, and I go up square root of 3 over 2 units, and I get this ordered pair here on the unit circle, where the terminal side of a 60-degree angle intersects the unit circle. We will continue in the next video.